So good afternoon, everybody. Thank you all for being here. My name is Zaid, Al-Ars, and I'm from Bluebee, a company specialized in high-performance genomics. And my presentation today, I'm going to discuss a working group that we have started within the OpenPOWER Foundation to bring together a lot of different players in the field of personalized medicine and to enable them with solutions within the OpenPOWER Foundation to accelerate the problems that they have and also enable their work in practice. You have seen a number of presentations today from different members of OpenPOWER that shown actually improvement in performance in various genomics pipelines, for example. And we would like to bring all those activities together and enable them from a technology point of view to make them faster and easier and cheaper. I will discuss as well, as part of this effort, our work in accelerating a specific pipeline that is specifically used in cancer diagnostics. So usually when I would like to understand a specific topic, I go to Wikipedia and I try to Google what kind of term I would like to know about. So Wikipedia says the field of personalized medicine is actually a customization of healthcare that eventually would help individuals to be treated based on their specific patient state. 4 different specific attributes that are being used for the personalized medicine application domain, that is predictive, preventive, personalized, and participatory. There are a number of different sources of information that can be used to identify the state of a patient within the personalized medicine application domain. So we can use information that is based on the molecular description of an individual or an organism. So we're talking about DNA data, for example, talking about RNA data. DNA sequencing is related to this issue. We can talk about the functional parameters of an individual. For example, blood measurement. For example, specific blood samples, imaging information. We can talk about behavioral aspects, which is what we talk about in general when we talk about measurement devices like watches that measure the activity of a person and otherwise. And bringing all these together actually creates a huge problem, computational problem, that eventually produces significant effort on the computational infrastructure to be able to address and to solve, in addition to a huge data problem that is, by accumulating all this information, would prevent institutions, organizations, and even hospitals that would eventually like to use this information to use them in their traditional diagnostics processes. Here I show just one sample of the growth of the genomic data information in the past 20 years and the exponential size of this information as it grows, and not taking into consideration any of the functional or behavioral data that we also starting to use in order to personalized medicine diagnostics. To address this application domain, we started talking within the OpenPOWER Foundation about initiating an effort to address the challenges within the personalized medicine application domain. And based on this, we started a work group to be able to bring together, as I said, technologies from different technology providers within the OpenPOWER Foundation and also different members that would like to use these technologies so that we can create solutions specifically designed for those who need them. It is the first OpenPOWER application domain specific work group that is not technology. So instead of having technology horizontal work groups, we're having the first application, so vertical work group. And we would like to have both sides of the equation taken care of. So we would like to design systems that are specifically created for those application, for the personalized medicine application domain. And on the other hand, we would like to optimize the applications themselves, the software itself, so that it can work efficiently on the existing infrastructure that is provided by OpenPOWER. The number of, we just started. We started about 4 or 5 months ago. We already have a large number of participants, 16 members, 10 organizations. And these are basically from different backgrounds, both technology and research and medical. We have, just a couple of months ago, we had a workshop where we brought together all these different partners, and we discussed together how we can go further. In order to show the possible benefits of this kind of, or the challenges that this kind of application domains would face, we would like to talk a little bit about the genomics field, because it is one of the most identifiable challenges that we see at the moment in the personalized medicine application domain, and it is also a showcase for what kind of improvements we can show for that field. Now, there are 3 different aspects within genomics that actually cause a big challenge in the field. The first one is the phase of generating the information. Here I show a figure, a graph that shows the growing size of the speed of generating, the reduction in price of generating information, genetic information, and the reduction in size in price in our hard disk storage capability or capacity. And you see that DNA sequencing is generating information at a higher rate, exponentially higher rate, as compared to our capacity to store that information. It's only a matter of time before this means that we are not able to store information, and many institutions at the moment decide actually to delete information that you already sequenced after they analyze them because they don't have the capacity to store them. But this will result eventually in a problem, a global problem, where you do not have really the capacity to store the information that you generate at a global level. And this is a problem that has been projected already. People actually predict, a couple of different researchers have predicted that the field of genomics will be the biggest generator of big data within the coming 5 years, something that we should keep in mind to be able to address in the coming years. The second phase of analysis within the genomics application, the genomics field, is the analysis of the information itself. I show another graph that shows the actual need for analyzing information within the application, within the genomics field, and the growth of our capacity to analyze it from a computing point of view. And again, you see that there is, of course, an exponential increase in the available capacity of computation and a higher exponential increase in the amount of analysis that is needed for the genomics field. And the final part is the interpretation part, which is after you've generated the data, after you've analyzed the data, you need to run a number of interpretation phases on your information. And we see that with the increasing amount of genomes that we are analyzing, that we are storing, with the increasing amount of information, you can do a number of multiple references, multiple genome analysis, and also need for visualization of this information that we're generating will actually create a shift in the coming 5 years from 5% compared to 95% of the price of analysis within the genomics field, from genotyping, which is identifying the mutations or the variations in the genomes, to 95% of the cost being dedicated to actually interpreting the data that we are getting. So the challenges are staggering, and all different institutions are facing them, and we would like to bring together all those different players in the field to address them head on. To give you an example of what we can do in such a field, we have analyzed a specific pipeline in the past couple of months, try to identify what are the bottlenecks in that pipeline, and try to provide solutions to enable speeding up the analysis of that pipeline and show some performance increase. The pipeline that we have chosen is the GATK pipeline. This is our first focus for our group. This is a pipeline, very well-known pipeline developed by the Broad Institute. It has been a great success for a number of different institutions and hospitals around the world. It is being used for cancer diagnostics all over the world, and all those institutions are desire to have reduction in the price of using that pipeline on their clusters to be able to treat more patients and to treat those patients at a lower price point. The computational complexity is huge. We're talking about every single patient, cancer patient, for example, coming in with about a terabyte of data for every single experiment, for every single biopsy. And we're talking about days to weeks of analysis time on a typical cluster where that an average institution has access to. It's a lot of waste of time for the institution, a lot of waste of money for society, and a lot of waste of energy if we are able to do this analysis, the same analysis, faster and cheaper. So the pipeline is divided into actually 5 steps: mapping, sorting, realignment, recalibration, and variant calling. Each one of these stages we have addressed, we have evaluated, and we provided solutions for each of them. And I will show you in each of these stages a number of solutions that we have provided. So in the mapping phase, we have used the algorithm that is now de facto standard. It's called BWMM. And this is a mapping algorithm that is basically tries to find out where the different pieces of the genome are located on a reference genome. We have used a number of acceleration approaches for this algorithm, and we were able to reach acceleration of up to 2 times using those hardware accelerators. This has been actually is available as IP, and we are describing this as part of our a document that will be released to the public so that everybody that is interested will be able to access it. Now, the sorting part, when we looked at the sorting and part of the analysis, we identified that actually much of the analysis that's much of the time that is being taken by this step is due to memory access, disk access, inefficient utilization of I/O, and we try to improve, optimize the performance of that code just by improving the code itself. And we were able to achieve significant speed-ups from 50 to 100 times improvement speed-ups just for this phase on its own, almost eliminating it from the computation time for the whole pipeline. Most of the work was not computational. Most of the work was just overhead. The next 2 stages, we try to address them in a generic way, not specifically identifying details of those stages, in the realignment and the base recalibration. And we identify that these 2 stages have actually utilized a lot of compressed information. So they zip data, store it in the disk, read it again, unzip it, do some analysis, zip it back again, put it back to disk, take it back out, unzip it, do some analysis, zip it back in, put it back to disk. And it continues that way, wasting a lot of time just zipping and unzipping on a processor that can do some other stuff. So we simply implemented an accelerated version of a gzip function and tried to improve the performance by just using such a generic accelerator. And we actually were able to reduce the execution time by up to 35%. And finally, the variant calling stage, which is actually a stage that is able to identify the mutations in the reads that the genome of the patient has. And we use a number of different acceleration techniques. We address this problem in depth. We use a number of different acceleration techniques with different hardware accelerators. And we're able to reduce it anywhere between 50% to 2 times acceleration, depending on the data set and depending on the system that we used. So bringing all these acceleration techniques and improvement and optimizations together, you can actually improve the performance of your pipeline of up to 2 to 3 times based on the original baseline that almost everybody around the world is using, which is a significant improvement to the baseline. Just to conclude, bring everything together, I would like to let everybody know that we have formed a personalized medicine work group. I would like to inform everybody that we are addressing pressing needs in the field that actually would help individuals and institutions solve their computational challenges within the personalized medicine application domain, that we have shown with a specific pipeline that you are able to achieve significant improvements in performance by just looking at your pipeline and identifying the bottlenecks and resolving them from a technological point of view, not necessarily from a biological point of view. And then finally, we are investigating a number of different future activities in our work group to accelerate other pipelines that are clinically needed by the users. Thank you very much for your attention.